Hey everyone, and welcome back to PrepFusion. So today we'll officially start our EMT subject. So we'll start with the first chapter, that is Electrostatics. So this will be the first lecture. So we have covered all the foundation, we have built all the base, all the foundation for the studying of this EMFT chapter. So we'll start with this lecture 1A, that is we learn about what is a charge and properties of a charge. I know you have learned a bit about charge in network theory, but we will learn here more about the physical properties of charge, not the mathematical properties, right? Also we'll understand different types of charge distribution. Also we learn the Coulomb's law. This mostly we have studied in 11th or 12th. This will be a good refresher for all of you guys. So let's start with charges. What are charges basically? Charge is a fundamental property similar to mass. What do I mean by fundamental property? This means it is an intrinsic property. Intrinsic property. Similar to mass. What does it mean? Basically, if there is some object, like this object is here, right? This will have some mass. This object is here. This will have some mass. Every object that you observe in the universe has some mass. There are a few objects which has negative mass, which we obviously haven't yet discovered, but that is for any other day. But for now, everything that you see in our life physically, everything has a mass. So whatever has a mass has a charge as well. It has a charge as well. Why it has a charge? Because whatever object that we see are made of atoms, and inside atoms there are neutron, proton and electron, and proton and electron have charges. Proton have positive charges, electron have negative charges. So everything that you observe has charge. So charge is everywhere. Charge is literally everywhere. Okay, and is always associated with matter. Wherever there is matter, wherever you see an object matter, it will have charge. Just like mass, charge is an intrinsic property that exists along with particles and cannot exist independently. Charge will exist with this particle only. It cannot exist isolatedly, like the charge of this particle is isolated somewhere else. No, it will exist with this particle only. Charge is a property of matter that allows it to produce and experience electrical and magnetic effects. Actually, charge produces many electrical and magnetic effects, the effects of which we will discuss obviously in this subject, and that will be helpful to invent new things. Okay, that also we learn. When a charge is stationary, it produces only electric field. So whenever a charge like this object is not moving, or inside this the charge, right? Charge is just stationary. Inside atoms, the electrons always keep on moving. Just for a second, assume that a charge I have of an object that is stationary. If it is stationary, it will produce electric field. Okay. So this you should know this. You should know this because this is the chapter 1 basically. So there is the electrostatic part. Whenever the charge is stationary, it is not moving. It is not moving. Okay. Then if a charge that is moving charge, it will generate both electric as well as magnetic effects. Okay, the moving charge creates an electric field as well as magnetic field. A stationary charge creates only electric field. A moving charge will create electric and magnetic field. Now when a charge is accelerated, here the acceleration was 0, that is velocity was constant. Here remember I am talking about velocity. Velocity, right? Velocity vector, not speed. Velocity vector is constant. Velocity needs to be constant. If the velocity is constant, that means it will only create electric and magnetic field. Now if the velocity is also changing, that is it has some acceleration. So if that particular charge has some acceleration, what will happen? Just hold on, I will just check if everything is yeah, everything is recording. If it also has an acceleration, it will produce electric field, magnetic field, and will also radiate energy. Okay, radiate energy in the form of electromagnetic waves. This will not learn here, but this is also good to know. This thing is good to know. This is, you have already learned in your class 11th and 12th. Just giving you a quick refresher. So in short, I have shown you here visually what is actually happening. That is, if my velocity is 0, that is charge is at rest, then it only produces electric field. If my velocity is constant, that means charge is moving with constant velocity, it will produce both electric and magnetic field. If my velocity is not constant, that means it is time varying, that means my acceleration is not equals to 0. If my acceleration is not equals to 0, that means it will obviously generate electric field and magnetic field. Also it will radiate energy. It will also radiate energy also. Okay. Now, like basic structure, few basic things we should know. Atoms. Matter is made up of molecules which in turn are composed of atoms. Atoms consist of subatomic particles like electrons, protons and neutrons. Inside atom we know there is electron, proton and neutron, and combination of many atoms make few molecules. In a neutral atom, the number of protons positively charged equals the number of electrons negatively charged, resulting in no net charge. So if the atom is neutral, it is said to be zero charge because the number of protons, whatever the charge amount is, will be equal to number of electrons, as the magnitude of the charges of protons and neutrons are same, just that they are opposite. The electron has negative charge, proton has positive charge. When an atom loses or gains electrons, it becomes a charged atom, ion. Okay, when it loses or gains electrons, it becomes a charged ion. This we learn in chemistry. Now you might say, sir, why it can't lose proton? It can't lose proton because proton is tightly bounded with the neutron, right? It is tightly bounded with the neutron, so we cannot generally remove protons, but electrons are actually revolving around the orbit, so removing electrons is easier than to protons. That's why here we say if the atom loses or gains electrons, not protons specifically. Okay, I hope you got the point. Now a few things about charges. It is generally represented with capital Q or small q is point charge, that is. Then SI unit of charge will be Coulomb. Charge is a scalar quantity and can be added algebraically. Okay, it is not a vector quantity. Charge is a scalar quantity. Like charges will repel each other, unlike charges will attract each other. Okay, unlike means if both the signs of the charges are different, that means plus minus will attract, minus plus will attract, but plus plus will repel, minus minus will repel. This is known as the Bohr's model of atom. Okay, this we know, and here there are protons, and like this we obviously will learn later on as well. But if I just take the proton out of this atom, right, and just observe the field, there we will generate a field, electric, that is known as electric field, that we will obviously learn in the next few lectures. That field will have a shape like this. Okay, it will be radially outwards. It will from the positive, always from the positive, it will be radially outwards for a proton or for a positive charge, positive point charge. For a negative point charge, it will be radially inwards. Everything will join here. All the electric field lines will actually join here. What is electric field lines? Don't worry, we'll learn this in the next few lectures. This I already told. In an electrically neutral atom, number of protons and electrons are same. Now when an atom loses electrons, it becomes positively charged. Why? Because if an atom is losing an electron, right, then previously the number of protons and number of electrons were same, but electron has gone, so number of negative charges has reduced, so my atom is more positively charged. That's why, because it has more number of positive charge protons than number of electrons, so my atom will become positively charged as number of protons is more than number of electrons, and vice versa. If atom gains electron, it becomes negatively charged as number of protons is less than number of electrons. Number of electrons becomes more, excess electrons. This is also known as, just hold on, this is also known as deficiency of electrons, and this is known as excess electrons. Okay, so the SI unit of charge I have already mentioned, and this I can cut out because this already has been mentioned, right? This is a very important point. The charge of one electron is known as 1.6 into 10 raised to power minus 19 Coulomb. This is a fundamental quantity that you should remember. Okay, this sign should be negative because electron possesses negative charge. This you should remember. This you should know. The charge of one electron, okay, will be minus 1.6 into 10 raised to power minus 19 Coulomb. This you should know. You can put it in your short notes. This we already know, right, from our school days. Now the total charge of a body after gaining or losing n electrons is given by plus minus ne, and charge is a quantized quantity because I cannot break electrons further, so it will be a multiple of this. Whatever the charge present in a body, it will be always a multiple of this number. It can never be like non-multiple of this number. It will be a multiple of this number. So after gaining or losing n electrons, the charge can be plus minus. So if I am gaining protons, then it will be plus ne. If I am losing the gaining electrons, it will be minus ne. Okay, so this much we know, this much we have got to know, that the charge, magnitude of the charge of electron is 1.6 into 10 raised to the minus 19 coulombs. You should know. If an object has a net charge of minus 1 coulomb, right, this should be minus 1 coulomb, the number of excess electrons it possesses. The object has minus 1 coulomb of charge. How many excess electrons can it have? Basically, I know, right? Charge, right? Charge will always be multiple of this any. Okay, so here excess charge is minus 1 and this is n, the number of excess electrons or protons. This time this is negative, hence this will be electron only, right? This I will replace with the negative charge because I know I have excess electrons. Minus 10 raised to power 1 by 19. So number of electrons will be 1 by 6 into 10 raised to power 19. So I will just quickly compute this. Just hold on. This actually will be 1 divided by 1 by 6 into 10 raised to power 19. So this will be 6 to 5 into 10 raised to power 16. Okay, this many number of electrons are excess in that particular body if its net charge is minus 1 coulombs. Okay, pretty simple, just to get you started with. Now let's start with the electrostatic. What is electrostatics? Basically, electrostatics is actually study of charge only, but charge at rest. So electrostatics is the study of properties related to electric charge at rest and it is under motion. We'll talk about under motion later as well, but for now mainly it is at rest. So basically, the electric charge should be independent of time. It should not depend on time. It should not be changing with respect to time. So in case of electrostatics, the charge, right? The charge will always be independent of time. Okay, charge always will be independent of time. So property, okay, this is correct. So let's move on to the next term. The term static refers to the study of objects that are at rest and not in motion. Not in motion means it is not a function of time. The term uniform refers to something that is constant and or unchanging throughout a given region. So you have to understand these two things. If static is there, that means it is not like it will not change with respect to time. So it will not be function of time. And whenever a uniform term you come across, uniform means it will be constant with respect to time. So constant with respect to space. Constant okay with respect to space. So that is the case here. So let's do a few questions like this. Like, can you tell me out of this which is static and which is uniform? Which of the vectors are uniform and which of the vectors are static? So here I observe that this is a function of space, x and y, the function of space, but this is not a function of time. So this, right, this will be static and this will be non-uniform. Why? Because this is a function of space. Again here, all these components are constant, so this is neither a function of time nor a function of space. So here this will be static and uniform, and this is actually a function of time but not a function of space, because space is not varying. So this will be non-static or time varying, I can say time varying and uniform. Okay, so you should understand the difference between static and uniform. We are just creating the base right now, just understanding few basic terms. Out of this, another basic term is conductors. Okay, you have worked with conductors because you are studying electrical engineering. Conductors. Conductors are materials that allow easy flow of electric charge, typically due to presence of free electrons. As on the outer shell, the electrons present, there are huge number of electrons present of a conductor. The transfer of electrons can happen easily. Hence, the current can easily flow. Right. So examples of conductors are what? Copper, gold, silver, aluminum, graphite. Graphite is a good conductor despite like it is a carbon. Okay, it is a form of carbon, but it is a good conductor. It has few special properties. Okay, so these are 5 electrical conductors that we know. Another thing that we should know is like here, main thing that you should know is electrons are lightly bounded. Electrons are lightly bounded. Electrons are lightly bounded. Hence, I will require less energy. Less energy required. Okay, let's come to this point. This point is insulators. Insulator materials are which through which electric current cannot easily flow. That is, electrons cannot easily be taken out. Okay, so basically here electrons are tightly bounded. Hence, I need more energy to move the electrons. Hence, the current flow to happen. So, good examples of insulators are glass, plastic, rubber, wood, and ceramic. These are few good examples of insulators. Now we know about properties of charge. We learn few more properties of charge. Charge can be transferred from one object to another through conduction or induction, or there is another method known as by friction. Okay, so charge can be transferred. Charge can never be destroyed, but it can be transferred from one object to another object. Charge is always associated with mass. For example, the mass of an electron is 9.1 into 10 raised to the power minus 3 kg. This you should know. This should be in your short notes. Okay. This you should know. Charge has magnitude but no direction, making it a scalar. Charge has magnitude but it has no direction. So hence, it is a scalar quantity. This way I already told you. Charge obeys the principle of superposition. The total charge of a system is simply the algebraic sum of individual charges. Charge is quantized, meaning it exists in discrete amounts of q equals to plus minus n. E is the E is the charge of a single electron. Okay, so it will be always quantized. It will always be basically integer multiple of this number, right? This properties you already know, just going through. Like as mentioned, right, charge can neither be destroyed, so hence charge is always conserved. Charge is conserved, meaning total charge in an isolated system remains constant. So if the system is isolated from the surrounding, the overall charge through that system will be constant. Electromagnetic field. A charge creates electric field in the space around it. When the charge is in motion, it also generates magnetic field. That is already we have talked. Invariance. Invariance is a very good property. Invariance is a very good property. What does invariance mean? The charge of a particle is independent of its velocity. Charge remains constant irrespective of the particle's motion. Okay, so whatever motion the particle is like going through, the amount of charge that particular object consists, right, it will be independent, right? So obviously it should not come in influence of any other object if it is isolated. First of all, it has to be isolated. Okay, isolated from everything else. And if the object is moving whatever speed, with the speed of light or with 100 meters per second, the charge will still be constant. Why is this property very interesting? Because one thing I will tell you, one interesting fact that you don't know, okay, about mass. Actually, mass of a particle, right, varies with velocity. We don't observe this because we generally don't go at very high speeds. But there is very interesting formula of the rest mass and mass in motion. So MO is the rest mass, the mass of a body when it is zero velocity. So V actually here with velocity V, when the mass actually goes, when the mass is not at rest, it is moving with a velocity V, then its actual mass in that motion will be m0 by 1 minus under root V by C whole square. C is the speed of light. C is the speed of light. Okay, so it actually varies. This is not in syllabus, don't worry, not in syllabus. Okay, but you should know mass is actually not invariance. So if I move in the speed of light, what will be the mass? My mass will tend to 0. That's why we can never never move in with speed of light, right? That is a thing. Okay, so our mass actually reduces as I move more and more faster. So this is a very interesting thing that you should know. So mass is a variance quantity, but charge is invariance. That means charge, if I had a charge of value q at rest, this will be same at motion. Okay, it will not change. Okay, it will no change, it will still be same, but mass actually changes. This is not in syllabus, just ignore this, just you should know this interesting fact. Okay, now let's come to the transfer of charge, basically how our charge is transferred. So charge can be transferred in 3 methods. First method is charging by friction. Okay, so this actually doesn't happen in metals, this mainly happens in insulators. So what we do, it occurs when two different materials are rubbed against each other, causing a transfer of electrons. If two materials, right, like this cloth, okay, uncharged cloth and this plastic rod are rubbed, right, what happens, the outer electrons are actually getting into contact. Okay, and there is some transfer of charge, because this few electrons will flow into this cloth and few electrons will flow out of this cloth to the plastic rod, as the electrons are experiencing some force. So the material that loses electron becomes positively charged, while the material that gains electron become negatively charged. Okay, so we have to rub it. As I rub it, what happens, it comes in contact, the electrons comes in contact, so few electrons are attracted from the other material and transfer of electrons happens. Okay, so basically here charge gets transferred, and the most important point in this transaction is that the final situation is both are oppositely charged, both become oppositely charged. What is the final situation? If this loses, let's say 3 electrons, this cloth loses 3 electrons, this 3 electrons is here, so this plastic rod becomes minus 3e and this becomes plus 3e, because it has deficiency of electrons, it has excess of electrons. So final situation is the object both objects get opposite charges. Okay. Overall it is neutral. Because if I add these two charges, it will be neutral, or whatever the previous charge was. Okay, this is the important point that you should keep in mind. Okay, or you can write in your short notes. Next is charging by conduction. So we actually here, right, we actually rub the two different objects. Here we don't rub. Okay, we just touch. Okay, only touch, no rubbing, and this actually happens between conductors only, no rubbing. Okay, so in conduction, charge is transferred through direct contact between two objects. So if I just touch two metals, okay, let's say this is, even though this is not a conductor, let's assume this as conductor and this as conductor. If I touch these two, just the charge transfers and that's it, right? So I don't rub this. Rub means this. Okay, we don't do this. So here charge transfer through direct contact between two objects. When a charged object comes into the contact with a neutral object, some of the excess charge from the charged object is transferred to the neutral object, causing both objects to share the charge. The most important portion is here, right? Both objects will share the charge. Whatever the initial charge, excess charge initially this charge rod has, right? If I touch this here, both of them will share the charge. It will not be like one will be positively charged and another will be negatively charged. So electrons directly don't, all the electrons don't get transferred to the other object. Some of the electrons, some, right, causing some of the excess electrons from the charged object to the neutral one. Okay. So finally what will happen is, if let's say one object has charge q1, other object has charge q2, finally q final on both objects will be q1 plus q2 by 2. Both will share the same charge. Okay, the signs of charges will be same. It will not be different. Previously it was different. Okay, so both will have same charge. Right here, same charge. Okay, now there is another method known as charging by induction. What does charging by induction means? So induction occurs without direct contact between objects. So I will not make the objects directly in contact with each other. That means there is no touching. A charged object brought near a neutral object causes a redistribution of charge within the neutral object. This creates a separation of charges, positive on the one side and negative on the other side. What happens is, if I have two objects here, right, and what happens, let's say I have a negatively charged object here. I will just keep this object near the vicinity of this object A. What will happen? This is negatively charged. So we know electrons actually, we'll study this later on, they have electric field. So this will actually produce electric field, and whatever the positive charges here, right, protons here, those will be attracted here. Although those cannot flow through the air because there is too much resistance, but they will be attracted on one side of the particular ball of the object, right? And due to this positive charges, all the negative charges will be attracted here. Okay, all the negative charges will be attracted here, which will actually flow here. Okay, which will actually come here because they are in contact. So what will happen, this overall ball will be positively charged and this overall B will be negatively charged due to this particular effect, induction effect. Okay, if a negatively charged rod is brought near a neutral metal sphere, the electrons on the sphere are repelled. So electrons will be repelled here. Let's assume that these two are in contact. So electrons are gone here and protons are attracted here, causing the side of the sphere closest to the rod to becoming positively charged. So this is closest to the rod, that is positively charged, while the far side becomes negatively charged. Grounding the sphere allows the negative charge to escape, leaving the positive charge, leaving the sphere positive charge. If I ground this, the electrons can escape, the negative charge will go 0, but positive charge will be there. Okay, so induction is also there. We will not do any numericals on induction. Mainly we will do charge by friction or charge by conduction. Induction we will do about few basic questions, right? So this is a question that you just pause the video and try it out by yourself. And this also you pause the video. We learned about conduction, we learned about charge by inductions. You just pause the video and try it out by yourself, and then after a break I will solve this question. So let's solve this question. A glass rod is rubbed with cotton cloth and the glass rod gains a charge of plus 19.2 into 10 raised to the power minus 19 Coulomb of charge. So this glass rod actually gains this much amount of charge and it is rubbed. So what kind of transfer is this? What kind of charge transfer is this? This is by friction, right? Transfer of charge by friction. Okay, calculate the number of electrons lost by the glass rod, because the glass rod gains a charge of this much. That means it has gained positive charge. That means electrons, it has been gone out of the glass rod, right? Electrons has been gone out. So for this, simple formula, right? A, the charge gained is plus minus any. As charge, it has lost charges, so it will be plus any. Plus any, okay? Plus n e. So this will be equals to how much? Q is 19.2 into 10 raised to power minus 19 equals to, it has lost charge, so it has gained protons, so it will be plus 1.6 into 10 raised to power minus 19. So what will be n equals to? N, right? This will be 10 into 2, so this will be 12, right? 12. So n will be 12. So it has lost 12 electrons. The glass rod has lost 12 electrons. Now determine the negative charge acquired by the silk cloth. Basically, whatever charge the glass rod has lost, right? Whatever positive charge the glass rod has lost, that will be the same, magnitude will be same. The same charge will be acquired by the silk cloth, but it will be negative because it has acquired electrons, it has excess electrons. So B, charge acquired by cloth will be minus 19.2 into 10 raised to power minus 19 coulombs. Okay, next, is there any transfer of mass from the glass rod to the silk cloth? Okay, given mass of electron is this, there is, right? Because electrons are getting transferred, so mass will also get transferred. As charge is always with mass, so electrons are getting transferred. The number of electrons that is being transferred from this rod, this glass rod to silk cloth, that will be equals to that multiplied the mass of each electron will be the transfer of mass. So if charge has been transferred, mass will be transferred, although it will be negligible, but still it will be transferred. So transfer of mass, right, delta m will be n times mass of electron. N is 12, mass of electron, this although you should know, remember, they will give you in the question, but you should also remember this, that is 9.1 into 10 raised to power minus 31 kgs. This is very, very low, but still this is some quantity of mass, right? So if I multiply this by 12, what will this come out to be? Just quickly multiply this by 12. 12 into 9.1. This will be 109.2 into 10 raised to power minus 30 kg. Okay, so this will be the transfer of mass basically. This all will be the answer for this particular third question. Let's come to the fourth question. Fourth question, three identical insulated spherical conductors are there, A, B and C. Three identical insulated spherical conductors are there. Okay, these are all spherical. If I can draw a sphere, okay, and see. So initially objects A and B each carry a charge of plus 3 microcoulomb. A and B carry each carry a charge of plus 3, not micro, sorry, millicoulomb. Fine. While C carries a charge of minus 6 millicoulomb. If I can somehow write it. Okay, object A is touched to object C and then separated. Object A is touched to object C and then separated. So these two are actually touched with each other and then separated. What will happen? Basically, charge will get distributed between these two, right? Charge transfer will happen through conduction. Following that, objects B and C are touched, okay, and separated. When objects A and B are brought together near each other, will they attract or repel? So after all this, this is asking the question. So first of all, I have to identify the final charges. So I'll just copy this whole thing. Okay. And I will say first, object A and B are touched together. If object A and B are touched together, the charge for the first part, charge in A will be equals to charge in B will be equals to plus 3 minus 6 divided by 2, because charge, like, they will share the charges. Whatever excess charge each one have, they will just share it. So millicoulomb, this will be minus 3 by 2 millicoulomb. Each of them will have minus 3 by 2 millicoulomb of charge. Then in the second part, here, right, QC, charge at the C doesn't change, not C, sorry, this will be C, this will be C, this will be B. B, the charge will be same, that is plus 3 millicoulomb, plus 3 millicoulomb. Okay. Next is second portion. So here again, after this event has happened, then following objects B and C are touched together. So object B and C are touched together. So this time, right, object B has what charge? B has minus 3 by 2. Sorry, B has 3, but C has minus 3 by 2. So again, charge will get shared between C and B. So this will be minus 3 by 2 plus 3 divided by 2. So this will be minus plus 3 by 2 divided by 2, that is 3 by 4 millicoulomb. So each of them will have 3 by 4 millicoulomb, and object A has already charged how much? Minus 3 by 2 millicoulomb. Right. So now what will happen is that what is it asking? It is asking when objects A and B are brought near each other. So if A and B are brought near each other, so A has finally 3 by plus 3 by 4 of charge, and A has minus 3 by 2 of charge, B has plus 3 by 4 of millicoulomb charge. If they are brought near together, will they attract or repel? Attraction or repulsion depends on the sign. They are of opposite signs, so they will attract, obviously. So option A will be correct. Then when objects A and C are brought near each other, A and C are brought near each other, will they attract or repel? A and C. So C has again positive charge and B has again negative charge, so they will also attract each other, right? They will also attract each other. If object B and C were brought together, we know, right, they were actually charge transfer occurred between them with help of conduction. So obviously they will always repel because they will have same charges and same sign of charges, so they will always repel, right? So object B and C will repel, A and C will attract, B and C will also, sorry, A and B also will attract. Okay, so that's it about basically about the this charge transfer topic. Now we'll understand different distribution of charges. So charges can be subdivided into many types, right? Charge can be discrete or continuous. Discrete means only one single charge. One single charge means only one single point charge, right? Point charge Q. Okay, this is a charge. If I have multiple point charges like 1, 2, 3 here, right? This is still known as discrete because still I can see that I have 4 charges here, system of charge. This is known as system of point charges. Now here, if I have a continuous charge means like discrete charges means what? Charge that exists as a distinct and separate quantity. All these are distinct and separate quantity. In certain cases, the charge is distributed over a region of space rather than concentrated at a point. So here it is totally distributed over this particular sheet of paper. This charge is distributed over this rod. Okay, this is not distinct rather than concentrated at a point. So all these are examples of continuous charges. So there are mainly 3 types of continuous charges: line charge distribution, surface charge distribution, and volume charge distribution. So we'll study all this, like we'll just know the basis of these 3, and obviously we'll derive many things of this 3 types of charges. So first let's study about point charge. A point charge is an idealized model of a charged particle where the size of the particle is considered to be negligible. It is almost zero compared to the distance over which it affects over which the effects of electric fields are measured. So compared to its own size, the electric field the distance through which the electric field I will measure will be negligible. Why is this so significant? We'll learn this when we will study about the electric field, and also just we'll learn about the Coulomb's law. Don't worry. Just you have to remember this: a point charge is just like a sphere, but of radius almost equals to 0, and if it is positive, electric field will go out, and if it is negative, electric field will come in. We'll learn about this later on. Don't worry about electric field direction. Okay, now if I have a system of charges, I will have multiple charges which are placed at different points, which I can easily identify, and they will interact with each other. So these type of arrangement is known as system of charges. Next is line charge distribution. So if it is distributed over a 1D object, just like a line or a curve, right? If it is distributed over a 1D object, then it is known as line charge distribution. One thing you have to understand: if the line charge density of a uniformly charged rod will be Q by L, or if it is not constant, right? If the line charge density is not constant, then this will not be uniformly charged. What do you mean by uniformly charged? If I am here, I will observe the same charge. If I am here, I will observe the same amount of charge. If I am here, I will observe the same amount of charge. If I am here, I will observe the same amount of charge. So everywhere I will observe the same amount of charge if it is uniform. So if it is uniform, right? If it is uniform, where did it go? If rho L is constant, If rho L is constant, that means it will be uniform. It is not varying, rho L is not varying with respect to space. If I am on this particular coordinate, rho L is same. If rho L, and this is a very significant thing, so do listen to me carefully here. If rho L is not constant, okay, then the field or the charge distribution will be non-uniform, because it depends this charge density, right? Why is this called density? Anything density. What does density mean? Since basic class 9th you learned, density means volume per unit mass. So anything per unit, right? So if I'm just dividing charge per unit length, if it is not constant everywhere, if it is changing with respect to my space, if I'm lying here, the charge per unit length is something else. If I am here, the charge per unit length is something else, then obviously I will call it a non-uniform distribution. Okay, I will call it a non-uniform distribution. Surface charge distribution, it is distributed over a 2D structure, not a 1D structure. So charge is uniformly spread over a surface. Now again, surface charge density will be this. The same thing I will follow. I will just copy and paste. If my surface charge density, now this is charge per unit area. Okay, charge per unit area, not volume, because charge is divided throughout area, not a simple curve, not a simple line. Okay, it is divided throughout area. Now if my rho S, right, is constant, it will be uniform. If my rho S is not constant, it will be non-uniform simply. Okay, next, volume charge distribution. Volume charge distribution, charge is distributed throughout a volume. Charge is distributed throughout a volume. So again, the same thing, it will be charge per unit volume, the charge density, and I will copy and paste the same thing only. Okay, if it is constant, then it will be uniform. If it is not constant, it will not be uniform, non-uniform, right? So this is the basic distribution. We'll learn more about this when we will study the electric field topic. Now let's come to a very important topic, that is Coulomb's law. What is Coulomb's law? Coulomb's law defines the electrostatic force between 2 point charges. Remember, the point charge is very important. Coulomb's law is defined for point charge only. Okay, Coulomb's law is defined for point charge only. States that the magnitude of the force between two stationary is also very important. Stationary electrically charged particles is directly proportional to the product of the charges, like the amount of charge that is present on those two particular point charges, and is inversely proportional to the square of the distance between them. So Coulomb actually derived this formula, that the force, like there will be some force between charges, just like mass. If this is a mass and this is a mass, we know there is some force, although this is not visible, but you know, right, there are two planets like our Earth and Sun. So Earth and Sun has some force between them, right? Gravity, we call it gravitational force, and like that's why the Earth rotates in orbit around the Sun. Okay, so similarly, two charge objects will also experience a force. It depends on the amount of charge and the distance between them. Okay, so basically this point is very important. It is Coulomb's law is only defined for 2 point charges, and I have defined what is point charge, so do keep this in mind. So basically Coulomb actually is telling us that the force between those 2 point charges, the force that those 2 point charges, they will experience same force but in opposite directions. So force direction I will talk about later. Let's just talk about the magnitude for now. So force will be proportional to the product of the charges and inversely proportional to the distance between the charges, square of the distance between the charges. Okay, so overall we have to keep a constant, proportionality constant, and that will be it basically. So that will define our Coulomb's law. This equation is very, very important. Do you need to remember this? No, you already know this. I think you have already studied this in your 11th. But do remember, this is only valid for point charge. This is not valid for any other distribution. Point charge. This is only valid for point charge. Okay. If charges have like signs, both positive or negative, they repel each other. If charges have opposite signs, they attract each other. So this thing I have already talked about. Okay, so the directions will be like this. If they are both plus, right, they will both repel each other. If one of them is plus and one of them is minus, one of them, like both of them will attract each other, both of them will come towards each other. The magnitude of the force will be same, but the directions will be just equal or just opposite. direction will be opposite. Okay, so this AR cap we'll talk about, don't worry, in details. Just you take care of this magnitude. And this K, right, K is also known as Coulomb's constant. This is also known as Coulomb's constant, and this has been determined experimentally okay. This has been determined experimentally. K is equals to 1 by 4 by epsilon naught epsilon r, and this is this, or you can write it like this also. What is epsilon r? I will talk about just in a second, don't worry. Okay, so they are just like couples. If both of them are same, okay, both of them are same thinking, they don't come together very well, right? So they don't come together very well. But if both of them are opposite thinking, right, someone is someone likes romantic movies, someone likes action movies, okay, so then the combination is good, then the couple combination is very good, then they remain together. If both of them like romantic, right, for the starting period it will be very good, the bonding will be very good, but afterwards it may fade away. Just joking, okay, just joking, just giving you an analogy. I know this is a very bad analogy, okay. So that is about this Coulomb's law and direction. So let's do a basic question on this. When the distance between two charged particles is halved, if the distance between two charged particles is halved, the force between them becomes. The force between them will be what? Distance is halved. So initially my distance, initially my force was K Q1 Q2 by R square. Okay. Now the distance between them is half. So if the distance between them is half, it will be R by 2 whole square, right? So basically this will become 4 times F. So the force will be more, 4 times. Force will be 4 times. So as closer they get, the force becomes more. But in what direction? It depends on the sign of the charges. It depends on the sign of the charges. Now there is one term that was present here that I conveniently ignored, is this term, right? This term, epsilon. This is known as epsilon. Okay. So this will talk. This is known as the permittivity of a dielectric medium. Epsilon. Okay, epsilon. This is pronounced as epsilon. Just hold on. Epsilon. Okay. So epsilon is basically the permittivity of a dielectric medium. Just you should know this basic thing, okay? Permittivity is a measure of how much resistance is encountered when forming an electric field in a medium. So it's same as resistance, okay? Let's say if a particular wire is of higher resistance, the current will flow, the current to flow will be more difficult. To flow the current, it will be more difficult. But if the resistance is lower, I can easily flow the current, okay? Just same concept here, okay? So it indicates how easily material allows electric field lines. I will come to electric field lines, don't worry. But permittivity tells that this charge, right? This charge actually generates the electric field lines, and how easily this electric field lines can actually flow through the near vicinity or the region at which it is present. How easily the field lines can flow. Okay, so that is what this permittivity defines. This is just a constant number, and the permittivity of a free space or vacuum is known as 8.85 into 10 raised to the power minus 12 farad per meter. This you should remember, just like this. This also you should remember. 9 into 10 raised to the power minus 9 divided by epsilon r K equals to this. This also you should remember. Okay, these two things are most common things that we will use. They will not give you this. Okay, it represents the ability of a vacuum to allow electric field lines to pass through. A vacuum has lowest permittivity possible, so it is best. Okay, basically lowest permittivity means it doesn't resist. Vacuum resists electric field lines very low, just like air. Vacuum or air is also same. Okay, so the relative permittivity is denoted as epsilon r and is dimensionless factor that compares the permittivity of a given dielectric material to a permittivity of the free space. So epsilon r will be the ratio of permittivity of that particular material divided by the permittivity of the free space. Basically that's why this is known as relative. That's why this is relative to the permittivity at free space. Okay, so I hope you got all this. These are basic things. This you already know these basic things. Now the most important thing is for air or vacuum, epsilon r will be 1. That is the lowest permittivity. Okay, and the for perfect conductor, epsilon r will be infinity. Basically, electric field inside a perfect conductor will be 0. This will prove later on, don't worry. Okay, so basically the range of epsilon r will be from 1 to infinity. It can never go beyond less than 1. Okay, because this is the best. Okay, if my charge is at vacuum, it actually provides the best least resistance for the electric field lines to flow. Okay, so I hope you got the point. Now that's why the force depends, like just important point to note here, the force depends on the medium that the charges are placed in. So although it also depends this q1, q2 and r square, Coulomb did define it, but it also depends on a third variable, that is this permittivity of the space, that Coulomb didn't tell that time specifically, but obviously he experimentally determined this, but it was in air or vacuum. For other materials it will change. Okay, so Coulomb's law summary is there, is the electrostatic force between two charges is independent of the presence of third charge. So few important points that you should know is, if I place a third charge here, okay, if I just placed a third charge, okay, let's say 2q, okay, of plus 2q. Now the force between these two charges, right, due to these two charges will not change. This will still be q square by r square. Okay, but this will also create a force on this charge, but that is for the force between these two charges. But if I place a third charge, this will not affect the force between these two charges. Okay, very important point. The force between two charges is only influenced by their magnitudes and distance between them, not by other surrounding charges. So the force due to these two charges will only depend on these two only, not due to any third charge. Coulomb's force is conservative, meaning the work done by the force is independent of the path taken if it only depends on the initial and final positions of the charges. So basically the work done due to Coulomb's law will be independent. Basically it will be conservative in nature. Why? Because overall force, if you observe the overall force in this system, right, it is actually 0, because this charge is giving this force here, this charge is giving this force in this direction, it is 0. So overall the work done will also be conservative in nature. It only depends on the final and initial places. Two charges must be at rest. For the Coulomb's law to work, the two charges must be at rest. If they are in motion, then obviously magnetic effect will also come into the picture, that we will talk about later on. A point charge, important point, a point charge does not exert force on itself. A single point charge, right, it cannot obviously exert a force on itself. It can exert a force on this point charge, but it cannot exert a force on itself, right? That's one thing. Here, if two charges are same sign, they will be repulsive in nature. One had to be plus. If two charges are of opposite sign, they will be attractive in nature. This, like we have talked, I think I have repeated hundreds of times now. So there is one important point, very important point. Do listen to me carefully here. Okay, you need to listen to me carefully here. Coulomb's law in vector format, most important format. So if I have been given, like, what is the force? Like, what is this F12? F12 is what? F12 is defined as force on 1 with respect to 2. Okay, due to 2, how much force am I receiving? That is how I define F12. Many teachers will define separately, differently. Okay, you need to follow one certain convention. I am following this convention, that F12 means that force on 1 with respect to 2. Force on 1 with respect to 2. F21 means what? F21 means force on 2 with respect to 1. F21 means force on 2 with respect to 1. So basically due to 1, how much force I am receiving on the second charge. Okay, R1 is the position vector of Q1, R2 is the position vector of Q2. R1 is the position vector of Q1, R2 is the position vector of Q2. Q1, Q2 with signs in this formula. So you should remember this formula. How do I define this formula? Basically, if you observe here carefully, what is AR12? AR12 is basically R1 minus R2. R1 minus R2. Why is this R1 minus R2? Just hold on a second. AR12, right? Yeah. So this, right, this, if both of them are positive charges, I need to find a vector that is in this direction. How do I find a vector in this direction? This will be what? This plus this will give me R2, but I don't want this. Actually, I want I want actually this direction. Okay, fine. So how do I get this? So R2 plus some X is equals to R1. Okay, so R2, so I'll write here R2 plus some X vector will give me R1. So I want this X vector. So what will be X vector? X vector will be R1 vector minus R2 vector. Okay, so you can understand why I wrote it here. So I like, what you need to understand is, you don't remember this, you don't mark this up, you just draw the point charges and you understand what is the direction of F12, and in that direction you find that vector. Okay, don't need to remember this, just draw the point charges, and I have just drawn the point charges. I have found a vector that is in this direction. Okay, which is a function of R1 and R2. Okay, don't need to remember this, no need to remember this. Okay, just draw the vector and write down the signs. That's it. Write down with the function of R1 and R2. That's it. Okay, so yeah, R12 will be this, and F12 will be this, and F21 will be this. Okay, so F21 will be of opposite direction than F12 because the forces that the charges experience are opposite signs. Okay, I hope you understand. Just the vector format, one thing to remember here, this A of R12 is just a direction. So if I want to write this in vector, right, what will happen is, this is vector, but this is not unit vector, so I have to divide by the magnitude as well. So this becomes cube. So don't fear when you see Coulomb's law in cubic format, because this is with direction, as this was R square only, but this is written in R1 minus R2 divided by the magnitude of R1 minus R2 whole magnitude of R1 minus R2. So this becomes cube actually. Just hold on a second. One thing I have to do, this will be R1 minus R2. 3 by 2, right? This magnitude, yeah, this is correct only, cube. Yeah, this is correct only. Yeah, magnitude of this particular component. Okay, so I hope you understood this point. It's very simple. Don't worry while solving the question, just draw the charges and write the directions by yourself, and then assume the directions. Don't need to remember all this. Okay, so let's do a few questions. This is the first question. A charge q1 is placed in a vacuum at the point 1, 0. 1, 0 is here. Determine the force acting on q2 due to charge q1 located at 0, 1. So q2 is located at 0, 1. So, and q2 and q1 charges are like, we are changing the values of the charges. Okay, so for case A, what will happen? For case A, what will happen? Basically, if I observe, both are of plus signs. If both are of plus signs, one is plus, one is minus, so obviously they will attract each other, right? They will attract each other. So q2 force will be something like this. Okay, so you have to use your intuition. No need to remember things. Obviously, if you remember, then it's fine. But why do that? Okay, if you can understand. So direction will be something like this. Okay, so the force experienced by q2 will be in this direction. Okay, so I have to write down in vector format only. So how can I get this direction? So what is this direction basically? So this direction, right? If I go, let's name this as position vector R2, and let's name this as position vector R1. Okay, like the direction will always be line joining them two. It depends whether in this direction or in this direction, that depends. Okay, but it will be always along the line joining these two. Okay, so this is, how will I write this in vector format? So direction, the force on 2 due to 1. Force on 2, no need to remember all these notations. You can do this blindly as well, but still I will do this. Okay, what is it asking us? Determine the force acting on q2 due to charge q1. Yeah, force on 1 with respect to 2. Okay, so force on 2 with respect to 1 will be what? Basically it will be like, I know the direction. What is the direction? What is the direction of this? Let's name this as x vector. X vector here. First I will move this R2, then I will move x2 x vector, then I will get back to this what? R1 vector, right? So x vector plus R2 vector should give me R1 vector. So this will be equals to what? This will be simply, x vector will be R1 minus R2 vector. So I know I have found out the direction. I can find like, what is R1? R1 is simply in this direction, right? What is this? This is AX cap, right? R1 is simply AX cap. Fine. Yeah, it is in ax cap direction. And R2 is what? In the y direction, right? In the y direction, minus ay cap. And it makes sense as well. If I break it down into two components, one will be going downwards, another one will be going this positive x direction, and this is exactly correct. So I know the direction of the force. Now I need to find out the magnitude of the force. How do I find out the magnitude? So magnitude of F21, right, will be simply k q1 q2 by r square, the magnitude. But this is not a unit vector, right? I need to find out the unit vector. So unit vector will be what? Unit vector of F R21, right, will be divided by the magnitude of this, that is by root 2. So what is the distance between these two? The distance is pretty simple, right? It is a Pythagoras triangle, so this distance will be root 2. So K is, this is vacuum, right? Vacuum means K will be 9 into 10 raised to power 9. Okay, this you have to remember. Q1 is 1 coulomb, and obviously you have to write the signs of the charges. This will be minus 1 coulomb. Okay, this will be minus 1, or you here, right, if you have already assumed the direction, what you can do, either you write here signs, okay, either you write this charges with signs, or if you already have assumed the direction, right, you just write the magnitude of the charges. Okay, just write the magnitude of the charges. This will be 1 microcoulomb and this will be 1 microcoulomb. Okay, divided by r square. R square is root 2 whole square. So this is 10 raised to power minus 6, 10 raised to power minus 6, 10 raised to power minus 12. This will be 9 into 10 raised to power minus 3 divided by 2. So 4.5 into 10 raised to power minus 3 is the charge basically. Okay, it is the charge. Now if I want to write this in vector format, how will I write it? F21 vector will be 4.5 into 10 raised to power minus 3 ax cap minus ay cap divided by root 2. Okay, so don't need to worry about all this, no need to worry about anything. Okay, just this direction. First assume the direction where they are going, then you write down the direction properly, then you write the forces. Okay, then you write the magnitude of forces. The signs I am not taking here because it is already been taken care of. Taken care of. Okay, here. So I hope you got the point. Now for the part B, can you do this as homework for the part B and C? B and C, can you do this as homework? B and C I will give you as homework. This you try to do by yourself. Okay, pretty simple. Just first assume the direction, then you write down the magnitude of the charges, then you write the total format, vector format of the force between the two charges. Okay, so let's do the next question. Next question is Coulomb's law in 3D. So a charge Q2 is placed in a vacuum at point R2. So if a charge Q2 is placed at the point R2, R2 is given, determine the force on Q2 due to charge Q1 located at point R1. Okay, located at point R1. Both are plus. So what will be the direction of the charge? So here, right, here actually this drawing and visualization becomes a bit difficult. Now you have to do a bit of digging actually. So if let's say I have a charge Q1 here, and like let's say this is Q2 and this is Q1. So this is at point R1 vector, position vector is this, sorry, not R1, R2 vector, and this is R1 vector, right? So how will they experience the force? Basically the force experienced by them will be something like line joining them, but as both of them are positive, right, this will be outward. Okay, outward. Okay, they will repel each other. So even though it is a line joining them, so let's assume this as origin. Okay, let's assume this as origin. They are in 3D. I don't care, they are in 3D. Okay, but I have two vectors. This is the origin point, right? So this vector is R2 vector and this vector is R1 vector. But I need this vector. How do I get this vector? First of all, let's assume this vector as, so what do I need? I need to find determine the force acting on Q2. So I need to find out this vector. So let's name this vector as x2. So if this vector x2 can be, this is parallel, right? I can place it here as well. So what I can derive from this triangle law, simple triangle law, is r1 plus r1 vector plus x2 vector is equals to r2 vector, right? r1 vector plus x2 vector is equals to r2 vector. So what I can say is, what will be my x2 vector, or the direction of x2 will be r2 minus r1. So you don't need to do anything with direction. You are automatically getting the direction, right? You are automatically getting the direction. So now I know. Now what is r1 and r2? So r2 is this, right? R2 is this. So I can directly replace this. So this is 0.5 ax cap plus 1 ay cap minus 0.5 az cap, and I will subtract this with 0.5 ax cap plus ay cap plus 0.5 az cap. Okay, so this will be minus ax cap, ay cap will be gone, and okay, az cap also will be there, minus az cap. Okay, so there will be minus az cap. Now this is there. Okay, now I need to find out the unit vector, right? Unit vector. So a r21 cap will be simply minus of ax cap plus az cap divided by root 2. And what is the magnitude of the force? Now everything is simple, right? I just need to find out the magnitude of force. I don't care about the signs of the charges. Again, is it in vacuum? It is in vacuum, right? So it will be k q1 q2 by magnitude of the r21 whole square. So this is simple, right? K is 9 into 10 raised to power 9 in vacuum. Q1 is 10 micro, so it will be 10 into 10 raised to power minus 6 whole square divided by magnitude of this. What is the magnitude? Magnitude is this, right? This thing is only a magnitude. If I take the magnitude of this will be root 2. This magnitude will be root 2. So this will be root 2 whole square. So this will come out to be what? This will come out to be 4.5 into 10 raised to power, this is minus minus 5, 10 raised to power 10 raised to power minus 10, right? So 10 raised to power minus 1 this into minus ax cap plus az cap divided by root 2. So have I remembered anything? Okay, I have to take the direction here, reference there. No, nothing. Just simple basic vector. I have used simple vectors. That's it. I can neatly write this. Actually, this should be here. Actually, this minus sign can come here outside. 4.5 divided by 10 basically. Okay, or I can write this as 0.45 into ax cap plus az cap newtons. Okay, this will be the answer. Okay, so just use your simple brains. First identify the direction, then you identify the magnitude, and then just simply complement these two, merge these two, and write the answer. Okay, so what have they asked? They have asked determine the force. So I have determined the force with the direction as well. So that's it basically for this lecture. This lecture was pretty good. Okay, we learned a lot of things. We learned the basics. So trust me, this type of analysis, right? No one will teach you. Everyone will teach you this analysis. What analysis? This one. This one everyone teaches. Okay, you assume this as reference. Okay, but when you go to solve the question, right, you may forget. I have taught you a foolproof concept that you'll never forget. You'll never forget this thing. So these two are homeworks. Try to solve, and yeah, we will start with next lecture that will be also on Coulomb's law and multiple things. Thank you for watching and happy learning.